Today, we are going to talk about efficient tokenization. My name is Bychkov, and this article was written by my colleagues, Fedor Chernogorsky, Sergey Averkiev, Alena Finagenova, and me. Selecting an optimal tokenizer is a crucial step in the development of language models, as it has a significant impact on both performance and efficiency. An inappropriate choice of tokenizer can lead to substantial performance degradation, making tokenizer selection an essential part of the model design process. A straightforward approach to evaluate tokenizers is to retrain the full model, a big model, with each candidate tokenizer and compare their performance. However, this method is computationally expensive, especially for large models, and it becomes impractical when a large number of tokenizers need to be tested. An alternative strategy is to retrain a smaller model using each tokenizer and evaluate performance using a standard benchmark such as MMLU. However, commonly used benchmarks like MMLU are not well suited for small models and tend to yield unreliable or poor results in this setting. To address this limitation, we propose to use a benchmark specifically designed for small models. This allows to make efficient comparison of tokenizers by training only small-scale models and selecting the most effective tokenizer based on their performance in a more appropriate evaluation setting. So this paper makes the following contributions. We introduce BabyMMLU, a benchmark data set specifically designed to evaluate the performance of small language models. We propose a methodology for tokenizer evaluation, enabling consistent comparisons across different tokenization strategies. And finally, we conduct comparative analysis of various tokenizers and to highlight their relative strengths and weaknesses. Small language models face several challenges that limit their effectiveness in evaluation tasks. First, understanding task format. Small models often struggle to interpret what is expected of them when multiple answer options are included or presented directly in the prompt. For example, in multiple choice format with lettered options, such as A, B, C, and so on. This format, commonly used in benchmarks, can be difficult for small models to process correctly. Second, small models also find it challenging to generate appropriate answers when questions are presented as complete sentences, rather than just as prompts where the answer is a natural continuation of the question. And third, due to their reduced capacity, small models often fail to produce correct answers just because they lack the necessary knowledge or generalization ability required to handle abstract or rare cases. So how can we address these problems? To overcome the limitations of small models, we designed BabyMMLU benchmark with several key features. First, it is cross-entropy based, which means that rather than relying on the model to select the correct answer by its numerical position, such as A, B, C. We compute the cross-entropy loss for each candidate answer. This removes the need for the model to understand or to interpret option labels, and instead this approach allows the model to focus on its ability to predict the most likely answer based on language modeling. Second, all questions in BabyMMLU are framed as sentence continuations. This format aligns naturally with autoregressive structure of language models and simplifies the task, especially for small models. No explicit answer choices are presented in the prompt. I will show you an example on the next slide. And finally, the benchmark is designed with relatively short and simple questions and answers. We avoided domains that require complex reasoning or specialized knowledge, for example, advanced science or high-level academic topics. The difficulty level corresponds roughly to general knowledge or early high school content. These features improve the efficiency of models with limited capacity, making our benchmark suitable even for small language models. Here you can see one BabyMMLU sample. For example, the question is in the binary numbering system, each digit makes one of, and there are different options, 10 values, 8 values, 2 values, or 16 values. Also, we specify the correct answer, which is third for this sample. So it's two values. By the way, BabyMMLU is written in Russian. Now let's talk about how we created BabyMMLU. The dataset was created in 4 steps. On the first step, human editors created a list of candidate samples for potential inclusion in the dataset. Then we asked GPT-4 to generate additional candidate samples. Approximately 20% of the final dataset was derived from GPT-4 outputs. On the third step, all candidate samples, both human and model generated, were manually reviewed and filtered by human editors. On the final step, we balanced labels to ensure that all answer choices had an equal probability of occurrence. It was done to minimize potential bias in model evaluation if someone wants to check it in option-based setup. Actually, it was not important for our setup because we used a cross-entropy based setup, and in this setup it is completely irrelevant the order of answers. We propose the following pipeline for evaluating tokenizers. Oops, sorry, it's a power. We begin with a source data set and sample 2 subsets. It is important to sample data with the same probability as they are present in source data set. Then we train the tokenizer using the first data set and tokenized the second data set using trained tokenizer. Then we train a model and evaluate it. The key idea behind this methodology, it is very important. I want to emphasize this. The key idea is that the model's performance, this model performance, reflects the quality of the tokenizer. So the question was how to evaluate tokenizer. The answer is evaluate the model, and it will correspond the quality of tokenizer. Why this works? Because by fixing all other variables and changing only the tokenizer, we can attribute differences in model performance to the tokenizer which we are evaluating. So this is the main idea. To evaluate the model and tokenizer, we propose the following procedure. Begin by evaluating each metric for every tokenizer or model. Here you may see some example. Each row is some tokenizer or model, and each column is a metric or normalized metric or a final score. So at the second step, normalize the values of each metric across all tokenizers. So we take the whole column and normalize it, for example, from the range from 0 to 1. And finally, compute the final score as a weighted sum or linear combination of the normalized values. The weights for metrics are assigned based on their relative importance. So in the beginning, you should decide which metric is more important, and then just make calculations. In the study, we considered several metrics for evaluation. The metrics we used in our analysis are highlighted in bold. Specifically, we employed bits per character, average characters per token, and BabyMMLU. We chose not to use tokenization time because the quality of tokenization was more important for us than the time taken for tokenization. And additionally, we excluded MMLU and RuMMLU and similar benchmarks from our evaluation because we found that for small models, MMLU and RuMMLU show almost the same results for different models. These results are very close to random choice. So actually, these benchmarks are almost useless in the setup with small models. An important aspect of our methodology is that we fix computational budget for each model training run. It is important for two key reasons. The first is that by setting a fixed budget, we ensure that it is limited. It's just a constant. If we had an unlimited budget, we could afford to train large models for each tokenizer, but actually it can be very expensive. So we propose a more practical solution, which is a limited computational budget. And the second idea is that fixed computational budget for each model training run guarantees that the comparison between different models is fair, because each model is trained under identical resource limitations. There are different ways how to set a fixed computational budget. For example, we just used a fixed time limit for each model's training run. In our case, it was a 12-hour training period for each model. And to calculate metrics for the trained model, you may use either the final checkpoint of each training run, or you may use the average across several checkpoints near the end of the training. Insights. Our analysis shows several interesting insights. First, BabyMMLU proves to be efficient both for small and large models. Then we found that vocabulary sizes smaller than 128,000 are slightly inefficient when measured by BabyMMLU characters per token and bits per character metrics. Regarding tokenizer frameworks, the sentence piece framework outperforms Hugging Face when applied to out-of-domain data based on the character per token metric. Here, out-of-domain data is the data in a language which was not present in the data set for tokenizer training. In contrast, Hugging Face's byte pair encoding algorithm performs better than the unigram algorithm when applied to in-domain data with respect to character per token metric. And very unexpected finding was that training with larger data sets, training tokenizers with larger data sets for the Hugging Face framework led to a decrease in the characters per token metric. It's very unexpected. And we assume that this could be due to some overfitting during training. And actually, it's an interesting area for further research. And conclusion, selecting an optimal tokenizer is crucial for achieving high model performance. In this work, we proposed an efficient evaluation pipeline designed to operate under limited computational resources. It offers practical guidance for selecting and optimizing tokenizers in resource-constrained environments. As part of our methodology, we introduced BabyMMLU dataset specifically designed for evaluating small language models with fewer than 1 billion parameters. Additionally, we conducted a comparative analysis of various tokenization frameworks and provided insights about their relative performance across different settings. BabyMMLU is available for download and further experimentation. We also plan to release tools in Python for working with this data set. Thank you for your attention, and we welcome any questions or feedback.
Thank you. Do we have questions from the audience? Yes, we have. Please.
Thank you for your speech. I have a question about dataset. You said that you are trying to restrict some hard tasks for models and not include reasoning tasks or scientific tasks. I think I can agree with scientific tasks, but nowadays some small models are improving, and even reasoning already is included in some models with size of 1.5 billion parameters. Do you think it's reasonable to exclude some hard tasks? Maybe we can add them in a restricted way to the dataset, so our dataset won't be outdated with new future results of small models.
Okay, thank you for your question. I believe that if you can get distinguishable results from any benchmark, then of course it is possible to use this benchmark in the evaluation. In our case, we get almost the same results, so that is why we excluded it. I hope I have answered.
Okay, thank you.
We had another question there, please.
First question, please. Thank you for your speech. And could you repeat, please? We can evaluate both tokenizer and model with your benchmark. Yes?
Yes, we actually we gather different metrics. We gather metrics from the tokenizer itself, and also we gather metrics from the model. We get all these metrics, and we attribute these metrics to tokenizer, because the model here is it's just some helper. It is not a final result. After performing this evaluating, actually this model can be moved to trash, because it doesn't give you any helpful, doesn't bring you any helpful information. Here the idea is that we are maximizing the performance of tokenizer. After we find the best tokenizer, then we can retrain a big model using this tokenizer, because here we are training just small model, which will be inefficient in comparison to a large model.
So we evaluate just tokenizer, and your benchmark is not suitable for evaluating models.
No. Yes, you're right. This pipeline was designed to evaluate tokenizers. Actually, you can use it for evaluating models, but this pipeline, you do not need this pipeline. You maybe need only actually this table, which is very simplified version of our methodology.
Okay.
So our methodology was designed to evaluate primary tokenizers.
Thanks.
Thank you. We had the question out there. Sorry? No, already no.
Hello, thank you for your presentation. I would like to ask, is it available, your best tokenizer for open source? Can we use it?
Could you repeat, please?
Is your best tokenizer available? Is your best tokenizer available for use in open source? Can we train model?
So
maybe
I'm not sure about this. Can you write me maybe in Telegram? I can find out the answer to this question.
Maybe it's available in open source in GigaChat Maya model.
Maybe. Actually, I need to ask my colleagues about this.
Okay, and as I understood, you have MMLU format, so you can evaluate a model, and it would be like performance of the model in Russian language. Is that right?
Could you repeat, please?
So it's like MMLU format, so you need to choose one answer from...
No.
Okay.
No. Here I talked about the format of this benchmark. Actually, it looks like BabyMMLU in this meaning that there are different choices, and the model should select one choice. But actually, the steps required to get the answer from model are completely different. In MMLU, just in MMLU, you construct a complex prompt, which is, for example, in here, it will be such approximately the following. In the binary, you are given a question. Please choose one of the following options. The question. In the binary numbering system, each digit takes one of and choices. 10 values, 8 values, and so on. Please answer the letter. Choose the letter. This will be the prompt. You put it in the model. Just get the letter and match the letter with the answer.
Yeah.
In our case.
Sorry.
Yes, in our case, we do completely different things. We put in model just this question. Just this question. In the binary numbering system, each digit takes one of, and that is all. And then we measure cross entropy of different choices. So we add here 10 values, mask these values, and compute cross entropy for this continuation. Then we repeat this process, putting here different answers and measure their cross entropy. And then we just select the answer with the smallest, with the smallest cross entropy.
Yeah, thank you. And we can use this data set and write the prompt for using it like an MMLU format with
Yes. We have already tried this, and actually, we tried it for small models, and it works very badly. If you have a big model, yes, possibly it will give you good results.
Thank you for your presentation. I have a question. You said that your dataset may be used for benchmarking tokenizers. Which tokenizers did you test? Only English language and Russian language, or some others? Because for some hieroglyphical languages, tokenizers are completely different. Will your dataset tackle this problem too?
Here our pipeline. Here is our pipeline for evaluating tokenizers. Actually, the idea was to train our customer tokenizer. So we, of course, we tested open source tokenizers, but the main idea was to train our tokenizer from scratch. We mostly we were focused on how to say European languages and Russian languages, and also languages of people who live in Russia. There are different languages in Russia. So we mainly focused on this. We didn't try hieroglyphical languages.
Oh, thank you.
But actually, you can apply this framework for them too.
Thank you for presentation. I have a question. You said that your pipeline is designed to evaluate tokenizer and performance should be comparable with bigger models. So have you calculated like some correlation between tokenizer with a small model and a tokenizer with a bigger one? And have you seen like model perform poorly on BabyMMLU and good on normal MMLU, and vice versa?
Yes, there is a table in appendix of our paper where you may find calculated metrics for big models. So there are BabyMMLU and just MMLU and raw MMLU. So you may see that for big models, they actually the values are in correlation. So you may use it for big models.
Okay, thank you.